In this video, we'll be going over Coulomb's law, as well as starting off our unit 6, which goes over charge, centripetal motion and acceleration, as well as gravitational laws and fields, and how to draw gravitational and electric fields. Alright, so let's get started. Coulomb's law is named after a physicist, that worked with charges. And a charge is really just a type of magnet. It's a type of electricity here. There's a proton, with a positive charge, which means it's just a unit, a positive something. And then an electron with a negative charge. And if one is positive and one is negative, they're going to attract. Alright, very similar to a magnet. That's why it's called electromagnetism, right? If both of them are opposite, they'll pull to each other. They'll pull together. But on the contrary, if both of them are the same, they'll push apart. Like you can see here, the positive and the positive here. You can see how it's pushing apart, right? And they'll exert the same force on each other. Because of what? Because of Newton's third law, right? Whatever force is being exerted here, so if we get force F in this direction, equally and opposite in this direction, we'll have a force F. We know that because of Newton's third law. And that's how charges work. And neutrons, they don't have any charge. It's just protons and electrons that deal with charges. So neutrons you won't really be working with much when you're going over Coulomb's law. And the formula for Coulomb's law, or what the actual Coulomb's law is, force is equal to K times the magnitude of Q1, magnitude of Q2 over R squared. And this here should really just be the force, because if you're putting magnitudes here, then the force also has to be the magnitude. But I'll explain that in a second, So what does this mean? This is basically saying the magnitude of the charge, So if one charge has a greater magnitude, so one charge could have 3 coulombs or 5 coulombs, right? And this, by the way, is a unit of charge. A coulomb. Coulomb. You remember it from our SI units video? Yeah. And then Q2, similarly, a charge with coulombs as a unit. So the greater the charge here for both of them, the greater the force is going to be, which makes sense, right? If they have a larger pull or a larger presence, they're going to have a larger attraction or repulsion, consequently. R here is the distance, which is basically saying that because it's divided by R squared, it's proportional to your distance squared. It's inversely proportional to your distance squared, Which means the farther apart you go, so if you have a D here, this will be your force. It'll just be force is equal to kq₁ q₂ over R squared. But if you go 2D apart, then it'll be over 4D. So your force will be over a fourth. So here it would be regular force, and here it would be 1/4 of that force. So distance is what this R represents. It's really just a way of saying radius between them. But think about it as distance, And that's a factor of R squared. And this is going to be in meters, right? And since it's squared, here it's squared. And then what are these two? This is a coulomb, this is a coulomb. So coulomb squared. So what unit does this K have to be in order for the units to match up to force, which is newtons? This K has to be in units of Newton meter squared per coulomb squared, right? That cancels out the coulombs and the meter squares. What is the value of this K? It's called Coulomb's constant, It has a value of 8.99 times 10 to the 9. And I just showed you why it's Newton meter squared per coulomb squared, right? Because otherwise your units wouldn't match up with what you have to get, which is a force here. So this is just a constant. It's just Coulomb's constant. You don't really need to worry about that too much because coulombs are large charges, okay? 1 coulomb is very large. You'll probably be dealing with picocoulombs and nanocoulombs a lot more than actual big coulombs. And this here would be the magnitude of this force, because here we have magnitudes, right? So you can understand that if one charge is negative, negative q1 times q2 times k over r squared, then your force would come out to be a negative, right? So negative forces here are attractive because that means that they have two opposite signs here, right? But if you have the same sign, like negative and negative or positive and positive, we'll get a positive force, which is repulsive. This here, though, is just the magnitude of the force, so we don't need to worry about direction or direction here. But if you had to look for direction as well, you'd probably remove the magnitude signs here, and then you'd be on your way. Okay, so now let's look at 2-point charges. A charge of 3 microcoulombs, okay, and negative 5 microcoulombs again sit 0.2 meters apart. Find the force between them. Force is equal to K times, so if you're just looking for the magnitude, let me just say here's the magnitude, okay? So then this should just be force magnitude. It's equal to K times magnitude of Q1 times magnitude of Q2 over R squared, right? K, we know that to be 8.99 times 10 to the 9 Newton meter squared per Coulomb squared times, so this is actually a lot of stuff, right? Let me actually write it over here. Okay, this times the magnitude of Q1, which is just 3 times. So this has to be in coulombs, right? We need to put the units in coulombs because the units of this K value here is over coulombs. So we need to make this also in coulombs. We can't have microcoulombs here. So if you remember what micro was, it was 10 times 10 to the negative 6, right? So times 3 times 10 to the negative 6 coulombs times here, we'd use a magnitude, so it'd just be a positive 5 times 10 to the negative 6 coulombs all over 0.2 meters squared. So the coulombs here can cancel out. Okay, the meter squared would cancel out with this meter squared. What are we left with? It's going to be, so it should be about 8.99 times 10 to the 9 times 3 times 10 to the negative 6. Or, you could also just do some regular multiplying, right? But if you're looking for the final answer, you probably need to use a calculator. And then you should get about 3.37125 newtons, which you can round up to 3.37. And since you know that both of them are opposite charges, it's attractive, okay? So the magnitude, if you didn't have the magnitude to understand that because you get a negative force, but if you're using only the magnitude, then you wouldn't really, you just have to deduce it from the question, right? If you see 2 positive charges or 2 negative charges, the force between them is going to be positive. If you see 2 different signs, force is going to be negative. Okay? Alright, so now let's try some more problems regarding Coulomb's law. 2 charges of negative 2 coulombs and negative 4 coulombs sit at 4 meters apart. Find the force between them and state whether they attract or repel. Okay, so force is equal to 8.99 times 10 to the 9 Newton meters squared per Coulomb squared times negative 2 coulombs. Okay, So let me just put the magnitudes here. I can just deduce whether it's attractive or repulsive from the signs, okay, times magnitude of negative 4 coulombs over 4 meters squared, which is just 16 meters squared. It's like this, right? So it just becomes 16 meters squared. All right, so this should give you about 8 coulomb squared, which cancels out here, times 8.99 times 10 to the 9 over 16. The meter squared and meter squared cancel out, and newtons. So this is about, let's see, 8 times 8.99 times 10 to the 9 divided by 16, or about 4.49. So actually I'll round it up to 4.5 because there's a 5 there after that. 4.5 times 10 to the 3, 4, 5, 6, 7, 8, 9. Which makes sense, right? Both of these would be 8, and then the 10 to the 9 would stay from here. So you can imagine how this would also become 10 to the 9. Okay? So now next what we're going to look at is this question here. Or before that, let's state whether they attract or repel. Since they're both negative, like charges repel. Okay? Unlike charges attract. 8 nanocoulomb charge and a 12 picocoulomb charge are 2 micrometers apart. So a lot of unit analysis you gotta look at here, right? And then if you have a distance of 2 micrometers, find the force. So I gave you some values here, but keep in mind you won't always have them, okay? So you do want to try memorizing these, but for right now you have them here. Okay, so force is equal to 8.99 times 10 to the 9. I'm going to cut the units here for a sec because it could get too cluttered. Times 8 nano times 10 to the negative 9 times 12 times 10 to the negative 9. All of that over 2 times 10 to the negative 6 squared, right? So over here, I can just cancel out this 10 to the 9 and this 10 to the negative 9. I'm left with 8.99 times 8 times 12, or 863.04 times 10 to the negative 9. And over here, I'm left with 4 times 10 to the negative 12, right? Because that just, I mean, you have to square both the terms. That's just how exponent rules work, right? And then, how can I represent that? So 10 to the negative 9 divided by 10 to the negative 12, that's just going to be, so I'll just put these terms out first, okay, times 10 to the third, right? 10 to the negative 9 minus negative 12, so 10 to the negative third. Because if this is in the denominator, this would go up here, right? So let me just show you what I did there. Basic exponent math, right? So this should give you about, let's see, 863.04 divided by 4 times 10 to the 3, or 215,760. 215,760 newtons of force, which is quite a lot, right? Yeah, it's quite a lot. And I think the main factor here is because of this distance, right? That really carried a lot of it because it was such less of a distance that this 10 to the negative 12 literally helped cancel out this here. Okay. Now let's try some more. 2 negative 3, or before that actually, let me just state the repulsion or attraction here. Positive, positive, repulsive, because they're like charges. Okay. Two -3 nanocoulomb charges feel a force of 300 newtons. How far apart are they? Okay, so force is equal to 8.99 times 10 to the 9, and then the units times -3 times 10 to the -6, or I can just use magnitude here, right? Because I'll be able to figure out this units later. I mean, their attraction or repulsion later by looking at the signs. The negative signs could just make it a bit more complicated. That's why I don't usually include them. I just do units, and then later I check what the signs are to see whether they repel or attract. 3 times 10 to the -9 times 3 times 10 to the -9. Because it's this thing squared, right? I could just write this as squared here. Divided by, well, r squared. We don't know that. But we do know the force is 300 newtons. So we're solving for something different here. Okay? 300 r squared is equal to 8.99 times 3. So actually, this would simplify, this term would simplify to 9 times 10 to the -18, right? Times 9 times 10 to the 9 times 10 to the -18. We know this is just going to be equal to these two can stay, but this is just going to make 10 to the -9, right? Exponent adding become 10 to the 9 plus -18. So 8.99 times 9 times 10 to the -9, and then that divided by 300, right? Then square root of that. So that should give you about 1.64 times 10 to the -5 meters. Or you could say actually 0.16, and then no, actually you could, yeah, this is fine. 0.16 wouldn't give you a lot of good units. That would just give you 10 to the -4, right? You could say milli, or milli if you go up, or if you went down you could say something else like 16 micrometers, but that's fine. You can leave it as it is for now. Okay? Now, a pair of charges feels 9 times 10 to the -9 newtons. So isn't that very close to our K value? That's actually very close to what our K value is. And that's our force. Actually, let me just write down force. Okay. You triple one charge and then double the separation. What is a new force? So if you assume that F is equal to K, Q1 times Q2 over R squared gives you this force. Then you understand that if you make Q1 double, right? So, sorry, triple, 3Q1 times Q2 over 2R squared. This would just give you 3 kq₁ kq₂ over 4R squared. We can separate this out as our force, right? Because we know that's what our original force was. And you can see this makes out to 3/4 of the force. So only 3/4 of 9 times 10 to the 9. So if I was to write it that way, 3/4 times 9 times 10 to the 9. Or I guess we could 27 divided by 4. About 6.75 times 10 to the 9 newtons. Okay, and that's it for Coulomb's law. So make sure to stay tuned for the other problems I'll be going over, which is harder and more complex versions of these, as well as centripetal acceleration and gravity between planets. Make sure to give me a like and subscribe so I can continue helping people like you as well as more people.